Hello there, this is Jude Socrates. Welcome to Multivariable Calculus. This is my video series for Math 5C at Pasadena City College. And we are now in video number 24, 2 dozens. So today we are going to start a new chapter. So we're going to begin by getting an overview of that chapter, what we are going to see over the next few videos. So I will see you at chapter 4, which begins on page 190. Here we are. So there are actually many new things that we are going to see in this chapter. Some of them we have seen, so to speak, on GeoGebra, except that we haven't exactly given a name to it. Okay? So we are going to construct what are called space curves, and we'll call them with the letter C. And to do that, we're going to need a new kind of function, which is called a vector-valued function in one variable. So it's written as this r of t over here. Okay? We are going to construct the contour integral, and it's written this way. It's actually back to a single integral over the curve C of a function in 3 variables ds, okay, where your function is continuous on this curve, and it can also be only in 2 variables. Okay, so of course more on that later. What does it mean if your function is a density function? Then as usual we will find the mass of this curve, which we can think of as a wire. Okay, more new stuff. We are going to construct what are called vector fields. So we now have 2 functions that have the arrow symbol, the vector symbol on top. Okay, so of course this kind of function is going to be very different from this kind of function. More vectors. We have the del operator, and we are going to construct the gradient field of a function of 3 variables, 2 or 3 variables, these guys over here. And that will produce a very good example of a vector field. Okay, we are going to construct, we're going to determine rather if a vector field is conservative or not, and if so, we will construct. That's where we will construct a primitive function for these vector fields. Okay, now why are conservative vector fields important? Because it makes it easy for us to calculate the work done by such a field along a curve. So we're going to look at that concept. How do you find the work done by a vector field? And when you have a conservative vector field, how is it possible to compute that work with very little effort as soon as you have this primitive function? Okay, so I actually decided to move Green's theorem to a later chapter, so I'm going to erase that later on. But anyway, here are some pictures of what we are going to see over the next couple of videos. Okay, so let's start with our new object, what are called space curves. And to create a space curve, we're going to need vector functions. Okay, so as the word implies, a curve. Okay, we have actually seen these when we constructed our solids in chapter 3. And whenever 2 surfaces meet, we get something that you might call an edge. Okay, and some of these edges are curved. Okay, so in general, we're going to call these space curves. Now, of course, some edges are actually straight. Like for example, if you have a box, then the how many are there? 12 edges on that box are of course straight line segments. Okay, but we will still call them curves, even though they don't really curve. Okay, how do you create a curve on the plane or in space? We will need a vector function. Okay, so again, the notation is r of t. Who is this t? It's an independent variable, and it will be from some interval of r. Okay, so maybe it's all real numbers. That's the best possible scenario. The output of this vector function, as the name implies, is a vector either in R2 or in R3. Okay, so what this notation means is that the x, y, and z components of your function are all functions of a single variable t. Okay, so of course we're going to see examples of these in a few minutes. Okay, so t is called the parameter of your vector function, and well, because it's the letter t, we can think of them as time. Okay, so vector, of course, it's something that you can see. You don't really see time. Okay, you can feel time passing by. Okay, so how do we simulate seeing time on a graph? We are going to show the direction in which a plane curve or a space curve is being drawn. Okay, so the graph, okay, of this parametric or vector function is, of course, our space curve. We will plot all the points with the given coordinates in the plane or in space. Okay, so we're not going to draw the arrow. We're only going to draw the tip of the arrow. Okay, so because otherwise, all we're going to see are arrows. That's a holy mess. Okay, you don't want to see that. Okay, all you want to see are the tips of the vectors. Okay, so we also say that R of t is a parametrization of the curve C, or R of t parametrizes C, or it's a shorter word, it traces C. Okay, so C is something which we will call a parametric curve. Okay, so instead of saying a plane curve or a space curve, we'll just call it in general a parametric curve. Okay, so let's start out with the easiest kind of curve, a line, which again doesn't really curve at all, but we'll still call it a curve. Okay, so here's an example of a Cartesian equation for a line, y equals mx plus b. Okay, how can you turn this into a parametric curve? Okay, so very easy. Because y is dependent on x and x does not depend on anything, we can make x our parameter. Okay, so x will be t, and t can be any real number. Okay, so y, we just replace x with t. Okay, so this is now a parametrization of that line. Okay, so instead of this equation, you have this vector notation. Okay, so let's go to GeoGebra and see how to graph this using the curve command. Something neat. All right, so we'll start with 2 dimensions, and the command is curve. All right, so here you go. We have 2 choices, and basically, you only have 2 expressions in the first choice, and that's because we only have x and y. And here you have 3 expressions. You have a z coordinate. Okay, so we'll use the second one in a few minutes. We'll stick to x and y for now. So parenthesis, and our x is t, our y is 2/3 t, 2t over 3 plus 4. Okay, so you have to include the name of your parameter, which of course is t, and a starting value and an ending value. Okay, so how about, well, we have an over 3 there, so how about from -3 to +3? Ooh, there it is. Okay, so yeah, y equals mx plus b. Okay, so notice that the slope is 2/3, as it should be. The y-intercept is 4. Okay, so which way is the curve being traced? Okay, so because our slope is positive and our x is t, it's of course going from left to right. Okay, how can we be sure about that? Well, we can play with the starting and ending values. Okay, so what if we just ended at 0? Ooh, we stopped at 4. Okay, so what if we ended at 6? Ooh, now it's a little bit further away. Okay, so I guess we can lower this, I'm sorry, just zoom out a little bit. Okay, there you go. So, yes, so this line is being traced from left to right. Okay, so we will be drawing arrows on our graphs. Okay, so I'm not going to bother with that now because that will just be a waste of time. Okay, so let's go back to PDF. All right, so in my diagrams, of course, I put the arrows that show which way the curve is being traced. Okay? So here we dive a little bit more into our parametrization, and we separate this vector into two vectors. One that has the coefficient p, and one that has only constants. Okay, so because there is only t in the first coordinate, you have 0 here for this constant vector. Okay, so we have this new way to write this parametrization. It is a multiple by p of this vector 3, 2, plus this other vector. Okay, so of course 0, 4 corresponds to the y-intercepts. All right, what about 3, 2? You go to the right by 3 and you go up by 2. Okay, so of course that represents some kind of a slope. Okay, but of course in this case that's a vector, so we can think of this as a direction vector for that line. Okay, so we plot that vector in our graph, and we can see, of course, that the line goes in the same direction as our direction vector. All right, so the vector with p next to it, that's the direction of the line, and the constant vector 0, 4, that's the y-intercept. Okay, well, the y-intercept is just one point on the entire line. Any other point will actually be a legitimate point that we can use to construct the vector equation. So we have 2/3 x plus 4. So if you plug in -9, 2/3 of -9 is, -6 plus 4, so we get -2. Okay, so another point on the line is -9, -2. Okay, and we can make another direction vector for the line. All you have to do is multiply by a non-zero number. Okay, so if you multiply by -4, you get this direction vector. Okay, so obviously, if a line has a direction, it better be a non-zero vector. You have to go somewhere. Okay, so this is a new way by which we can parametrize our line. Okay, so we give it a second name. Okay, we call it R3 of t. So R2 of t is what we wrote in the previous page. Okay. All right. So that is, of course, the general syntax of our curve command. And again, you can play with the endpoints. All right. Now, because our vector is now negative, what was it? -9, -12, -8. Our line will now be traced in the opposite direction. Okay, so instead of going left to right, this parametrization R3 is going to trace it from right to left, all right, in the opposite direction. Okay, so let's go to 3-dimensional. All right, so let's generalize what we saw for lines on the plane to create lines in space. Okay, so how will we do that? We will fix a point x0, y0, z0 in Cartesian space and a non-zero direction vector. Okay, so our parametrization for that line, r of t, will be the vector corresponding to this constant point plus a multiple t of the direction vector abc. Okay, so of course t will be any real number. Right? The parametrization for the line is not unique. We can have another one. Okay, so let's call it, let's say, s of t. So let's change the zeros to ones, and let's pick different letters for the direction vector. How do we know that we also have a correct parametrization for the same line? Well, let's start off with the direction vectors. They better be parallel to each other. Okay? But what about these constant vectors, the points passing through the line? Okay? Well, if you're living on a line and you walk to any other point on the line, then you should be facing in the same direction as the direction vector or in the exact opposite direction. Okay? So either way, the vector that you form from where you are to any other point has to be parallel to the direction vector. Okay? And since these two vectors have been verified to be parallel to each other, all you have to do is check that the difference is parallel to one of them. Okay? What about the direction that the line is being traced? Well, if the second direction vector is a positive multiple of the first, then the two parametrizations are tracing the line in the same direction. But if the multiple is negative, you trace in the opposite direction. Okay? You can't multiply by 0 because otherwise you'll get the 0 vector. Oh, no, no, no. All right, so let's make our first problem. We're going to create a line in space. All right, today's first problem. Find a vector equation for the line through the point -5, 7, 3 and the point 1, -2, 6. Okay, so these are obviously two different points. So according to Euclid, there's exactly one line passing through these 2 points. Okay, well, all we need now is a direction vector. Okay, so who is going to be our direction vector? Oh, look, I have a vector ready over here. Well, we know how to form a vector, right? You just subtract these coefficients, let's say, from these coefficients. Okay, but of course you have to make sure that you're doing it in the correct order. 1 minus 5, 1 plus 5 is 6. And then you have -2 minus 7, so -9, and 6 minus 3, or +3. Okay, so interesting. We have a direction vector, but is it coincidence that they're multiples of 3? Maybe, maybe not. Okay, so of course we can simplify it if you want to, or we can use the direction vector. You reduce all of them by 3, so you'll get 2, -3, and 1 as our direction vector. Okay, so we are now ready to create our vector function. R of t will be, we will need 2 vectors. So we will need a constant, so choose either of these points. So we can use -5, 7, and 3. And we will need our direction vector. So we will need p times this direction vector. Okay, so let's go now to GeoGebra in 3 dimensions and we will plot out this. All right, here we are. So let's draw our curve. And I wrote it as 2 separate vectors, but in curve you kind of have to combine the 2. So we will have -5 plus 2t, 7 minus 3t, and 3 plus 1t, or 3 plus t. Okay, t will go from, we can use the same values as last time, -3, 3, and there is our line. Ooh, it's getting away from us. Okay, so let's zoom out a little bit, right? So that is our line. But of course, because we're only going from one number to another, you get a line segment, okay? I honestly have not played with infinity or negative infinity and space curves because, who cares? You can always zoom in or zoom out, okay? Let's plot those 2 points so that we can check that the line actually passes through those 2 points. Okay, so we have -5, 7, 3, and boop, yes, of course, it better be there because we used it as -5, 7, 3 right there. And the second point is 1, -2, 6. Are you there? Yes, you're there. Okay, so there is point B. Okay, so yeah, so notice though, okay, in what direction is the line being drawn? Okay, we are going actually from B to A. kind of going backwards. Okay, and yeah, let's check. Okay, what if you make the 3 small? Let's turn it into 1. What's going to happen? Aha! So wait a minute. Am I wrong then? Yeah, I am wrong. It is going from A to B. And that is why playing with these endpoints can verify whether your suspicions are right or wrong. Okay, so if we made it longer instead, okay, now it's beyond B. Okay, so we are going from A to B, but of course, because our interval is longer, it is longer than needed. Okay, we come from before A and we go past point B. Okay, one of the things we're going to need is, well, what if you want only the line segment from point A to point B? Okay, how are we going to make it start at A and finish at B? Okay, so one way is to play with these parameters, of course. Okay, so we already know that if you stop at 3, whoop, you're there at B. Okay, how can we start at point A? Well, point A is minus 573. So obviously we need to make P 0. Okay, so P will go from 0 to 3. There you go. And it looks like a very long dumbbell. Okay, so that is our line segment from A to B. What did we say? You can play with the point that you're using. Okay, so you can make another parametrization that starts at B. Okay, so you can have 1 plus 2p, negative 2 minus 3p, and 6 plus p. Okay, and what about our parameters? Okay, so this time we want to start at B and we want to finish at A. Okay, so will it still work if we go from 0 to 3? Let's check. Oh, check it out. Let's hide this. We seem to be going in the wrong direction. Why is that so? Okay, because we got the direction vector by going from A to B. So if we want now to go from B to A, we have to reverse the direction vector. Okay, so one way to do that is to reverse all the signs here. Okay, so minus 2 plus 3 and minus 1. Are you going to work? Boom! Okay, there you go. So this takes us from B to A. Okay, let's go back to from A to B. Okay, does it have to be 0 to 3? Okay, well, one easy way by which you can create any line segment is to just make P go from 0 to 1. Okay, so, but what about the rest of the curve though? Okay, this time you have to go for the full vector from point A to point B. Okay, so you remember how we divided by 3? Okay, so this time you have to include that factor of 3. Okay, so I'm going to hide this and let's do curve. So minus 5, and instead of plus 2t, I'm going to multiply the 3 back in. So 6t, and then 7 minus 9t, and then 3 plus 3t. Okay, so this time t is going from 0 to 1. There it is. Okay, so that's exactly the same line segment from point A to point B. All right, so let's go back to our PDF and we're going to look at curvier curves. Okay, so let's talk about circles. Okay, we are going to construct circles, and the idea is to think of trigonometry. Okay, when you're on the unit circle, the coordinates can be labeled as cosine theta, sine theta, right? Well, if you only want a full circle, then you go from 0 to 2 pi. Strictly speaking, though, when you reach 2 pi, you're really back to 1, 0, right? So you can technically remove that endpoint and make this an open parenthesis instead of um, a square bracket. Okay, but of course, in GeoGebra, you won't be able to do this. Okay, so you still have to write it as 0 to 2 pi. Okay, so we can use the curve command to create this circle, just like we did for the line segments. Okay, so let's generalize this a little bit to circles on the Cartesian plane. If your center is at HK, and you want the radius of your circle to be A, then you can create the parametrization HK plus A times cosine theta sine theta, where our parameter theta is from 0 to 2 pi. Okay? A circle can be generalized into an ellipse. Okay? So we can think of the ellipse centered at HK, and you have the denominators, I hope you remember your pre-calculus, a squared and b squared, where a and b are non-zero constants, which are different from each other, let's say. Okay? If they were the same, you would get back the circle. Okay? So the only difference now here is that that coefficient cannot stay outside. Okay? Because it will now go only on the x, because on the y, you will get b. Okay? So, of course, why this works is again because of trigonometry. Okay? If you solve for x and y, x is h plus a cosine theta. Y is k plus b sine theta. Okay? Isolate cosine theta and sine theta, you'll get x minus h divided by a as cosine theta, and y minus k over b as your sine theta. What can you do with cosine and sine? The trig identity. Cosine squared plus sine squared equals 1. And that's exactly the Cartesian equation of this ellipse. Okay, so here's our second problem. Let's find a vector equation for the right half of the circle. X minus 5 quantity squared plus y plus 3 quantity squared is 16. Okay, so let's identify our points. Where is our center? So I believe it is at 5, negative 2. Okay, and what is our radius? Our radius A is, it looks like it is supposed to be 4, not 5, but 4. Okay, so according to our template, our R of T should be only 2 coordinates. So we will have the center going over there and our trig going over here. Okay, so our center is at 5, negative 2. Okay, and let me scoot it over there. That's better. And we have our 4 times cosine of theta. I'll just use t. And sine of t. Okay. Now, the $1,000,000 question is, what is our domain though? Okay. We only want the right half of the circle. Okay. So t will be from, should it be 0 to 2 pi, that's going to make it a complete circle. Okay. So if you want the right half, okay, so the right half should go from down here to up over here. Okay. So what are those angles? You start pointing down. That should be negative pi over 2. And you rotate until you're at positive pi over 2. Negative pi over 2 to positive pi over 2. Okay. So let's pretend I'm in the classroom and somebody actually says, wait a minute, can't it be 3 pi over 2? Right? Because pointing downwards is also 3 pi over 2, correct? Yes, you would be correct. But now let's think about the rest of the domain. You start at 3 pi over 2. You rotate counterclockwise until you get 2. That's not 0. That's 2 pi. Okay? And you keep going until you get up here. That's not pi over 2 anymore. Okay? That is 2 pi plus another pi over 2. So that is 5 pi over 2. Okay? So we have two possible answers. And infinitely many more. But let's just write two of them. Or we can use the interval 3 pi over 2 to 5 pi over 2. Okay, let's check our work in GeoGebra. And we're back in 2 dimensions. We don't need that line segment anymore. Let's draw the circle. X minus 5 squared plus y plus 2 squared equals 16. Okay, there is our beautiful circle. And we only want the right half. Okay, so we said our curve will be, and you know, so that you don't lose your place, here's what I do. I put up the skeleton. So in this case, we're in 2 dimensions. So x, y, parameter t. And I go ahead and put the endpoints. Negative pi over 2 pi over 2. Okay? So this way, all I have to do now is fill in the x and the y. Okay? Again, combine the two vectors. 5 plus 4 cosine of t and negative 2 plus 4 times sine of t. Ooh, there's nothing there. Well, that's of course because I should hide the circle. Ooh. Okay, so of course this was right behind that circle. Okay, so we only get the right side of that circle. Okay, so that's with the domain from negative pi over 2 to pi over 2. Don't worry, it will come back. So if we change this now to 3 pi over 2 and finish at 5 pi over 2, it's exactly the same curve. Okay, so yeah, scoot back over. Yes. Okay. Okay, I'm going to challenge you a little bit. Negative pi over 2, pi over 2. Okay, so that is, yeah, that's a natural way of thinking about it. Okay, but what if I said, I'm going to tie one hand behind your back, and I'm going to say, I don't want you to use these pi over 2 nonsense. I want you to go from 0 to pi. Okay? So, 0 to pi. Okay, why 0 to pi? Well, that's how long the interval is, right? Whether it's minus pi over 2 to pi over 2, or 3 pi over 2 to 5 pi over 2, that's 0 to pi. Okay? So, you should be able to draw this half circle if your parameter is only going from 0 to pi. Okay, so what should we do now? Okay, will it still work if we did 5 plus 4 cosine t and negative 2 plus 4 sine of t? No, of course not. Now we have the upper half of the circle because our t is going from 0 to pi. Okay, so wrong, that is not a correct answer. Okay, so what should we do instead? Okay, well, we can still think geometrically. Okay, we want to start at 5 minus 2, but instead stay there and go down. Okay, go down by 4. Okay, So we now need a trig function that will have value of 4 at t equals 0, and that's what we put on the y, forcing it to go down instead of up. Here, the 4 cosine makes you go to the right by 4. Okay, so I'm going to bring it back. Okay, starting at 5 minus 2, this answer will force you to move to the right by 5 at t equals 0 and stay at minus 2 for y at t equals 0. Do you get it? So this cosine is going to have to move to the y coordinate. Okay? And instead of plus, it's going to be a minus. So minus cosine of t. Okay? So this will force that coordinate to go down by 4 at t equals 0. Okay? It should go up by 4 at t equals pi. Is it going to do that? Yes, because cosine pi is negative 1, negative 2, plus 4. Okay, so if cosine moves to the y, that means that sine should be the one for x. Okay, so is that gonna work? Yeah, okay, so at 0 you don't move, at pi you don't move, but what about in between, pi over 2? Okay, you want to go to the right by 4. Sine of pi over 2 is plus 1, so you do get 5 plus 4. So I believe that that is the right answer. I hate it when it does that. So, okay, there you go. Let's see if it does that. If it's, okay, it's, I hate it. Absolutely, totally hate it when it does that. Let's try it. There you go. Okay, so that is, the negative 2 got lost. I thought, wait a minute, it moved. Minus 2, minus 4. There you are. Okay, so let's check. Yep, that's the full circle. And that is the right half of the circle, where our domain is now going from 0 to pi. All right, now for something very different. We're going to take a look at the elliptic helix. So its parametrization is given by 3 cosine t, 2t, 5 sine t. Okay, so in the PDF, we see what's called the standard helix, where it is a little bit more boring. Let me just write it over here. For a standard helix, you just have cosine in the first coordinate, and then in the second coordinate, you have the sine by itself, and in the third coordinate, you have t by itself. Okay? So cosine sine, that's what we do on the unit circle, okay? But the third coordinate is t, okay? So as you go around the circle, you're basically just winding around the z-axis, okay, in both directions, okay? So we have a variation of this. We keep the cosine in x, but we move sine to the z, and we put the linear term for y. Okay, so we now have different coefficients for cosine and sine. Let's see what that does to our blades. Okay, back in 3 dimensions. So let's do curve. Let's look at the standard helix first. So cosine of t, sine of t, and then t. Our t is going from, how about negative 5 to positive 5? Ooh, okay. So there is our standard helix. Okay, so it's a spiral. Okay. If you look at the top view, you see our unit circle. And there it is. Let's look at the side views actually, the front and the side views. Here is the front view. Okay. So in the front view, if you turn your head sideways, actually sideways this way, so that the z-axis, the positive z-axis is to your right. Okay? I'm sorry, you want, okay, so I guess we should be rotated. That's all right. This is basically the sine function, okay, except it's upside down. Okay? And similarly, if you look at it from the side, okay, so let's look this way so that positive x-axis. There you go. So now when you turn your head this way, that's the cosine curve. Okay? And of course, that's because the x-coordinate is cosine, and earlier the y-coordinate is sine. Okay? So of course, we can see more of the helix by playing with the endpoints. We can make this a 10, and of course, it's going to go much, much higher. Okay? All right. Now, of course, if you want to see one period of the helix, okay, just like in trig, we will go from 0 to 2 pi. Okay, so about 6.3. There we go. So you start at 1, 0, 0, and then you climb around until you get to that point, of course, will be directly above your starting point. Ooh, isn't that neat? Okay, so that is our standard helix. Goodbye. Let us now draw elliptic helix. Okay, so we have curve 3 cosine of p, and then 2p, and then 5 sine of p. I'm ignoring my suggestion earlier. T, let's go again from -5 to +5. Ooh, okay. So we now have a helix which is winding around, that's the y-axis. It's winding around the y-axis because that is where we have our linear term, 2t. Okay, so of course, if we look at the, what is this? That's the side view. We see what looks like an ellipse. Okay, hence an elliptic helix. Okay, so we're smart. Again, think about the Pythagorean identity, cosine squared plus sine squared. So to isolate cosine, you need x over 3. Okay, so we have x squared over 9 plus, that's our cosine squared. Y is, sine is y over 5, so y squared over 25 equals a 1. Ooh, I'm sorry, that's not y. Silly me, that is a z. You're probably laughing at me right now. There you are. Okay, so that elliptic helix, okay, lives entirely on that cylinder. Okay, so that's a lot like the diagram that we see on the first page of this chapter. All right, for our final example, I'm going to be efficient. We're going to keep that elliptic cylinder that we just saw. And we are going to find the parametrization for the intersection of that cylinder with a plane. Okay, 2x plus 3y minus 5z equals 4. Okay, so when you take a plane, when you take that cylinder and you cut it with a plane, you will get something that looks also like an ellipse, except it is tilted. Okay, so before we solve this problem, let's go back to GeoGebra and see what that curve is like. Okay, so we want 2x plus 3y minus 5z is equal to 4. Ooh, okay. So that is our plane, and I guess we can zoom in a little bit. Ooh, okay. So I hope you're convinced that it does look like an ellipse, doesn't it? Okay. In fact, it is. I believe it is. Okay. But it's a little bit challenging to actually prove it. Okay. It's actually something that you can do with linear algebra. So for those of you who are taking, who are going to take Math 10, linear algebra next, or maybe you've taken it already, some ideas from there can actually prove that what you get here is an actual ellipse. Okay, so let's go back to our workroom and let's find the parametrization for this. All right, so how are we going to do this? So actually, the helix is already hiding part of the answer in plain sight. Okay, why is that? Remember how we got this equation because our x-coordinate is 3 cosine t and our z-coordinate is 5 sine t. Okay, so in general, every point in your elliptic cylinder can be expressed as x can be 3 cosine t and z can be 5 sine t. What about y? Y can be anything. Okay, so that's the key. X will be the same as before, 3 sine of t, and z will be the same as before, 5, our x is cosine. Okay, but actually, could it be sine? It could actually. They can be interchanged. So z will be 5 sine of t. Okay, well, what about the y? What about the y? Well, y, this point, also has to be on the plane. Ooh, let's check it out. We know who x and z are, so now we can solve for y. Ooh, what is y? Y is 1/3 of what? Of what? We need 4 minus 2x plus 5z. Okay. If only we knew who x is. Oh, right there, of course. X is 3 cosine t, and z is 5 sine t. Ooh, another 5. Okay, there we go. So, of course, we can simplify that into 4 minus 6 cosine plus 25 sine. Okay, so there we go. We now have our y coordinate, which we can copy over here. Don't forget to divide by 3. All right, so let's go back to GeoGebra and see if this curve matches that ellipse that we. Okay, and we already have most of what we need over here, so let's duplicate input and change the y coordinate into 4 minus 6 cosine of t plus 25 sine of t. Except we need to divide the whole thing by 3. And yeah, it already looks correct, and that is because our domain is more than what we need. Okay, so you only need one complete revolution, so we only have to go from 0 to 2 pi, about 6.3. Yep, there we go. Okay, so as before, if you only want part of it, then if you want half C's, okay, how about up to 3.14? Okay, so that's only the upper half of that curve. Okay, but no, we want the whole thing. So we will go all the way up to 6.3, 2 pi. All right, so there is our ellipse. Okay, unfortunately, this parametric curve does not exactly show that it satisfies the equation of an ellipse. There are too many coordinates. Okay, an ellipse is supposed to be just in x and y. What's the z doing there? All right, so I guess that's it. We have reached the end of our video, one of our longer ones, almost 50 minutes. So next time we are going to look at the derivative. The derivatives of these vector functions. All right. So until then, enjoy the rest of this beautiful day. Bye.